In the previous video, I showed you the impact of changing one lower bound or one upper bound and how it can be calculated using the reduced cost, right? Where reduced cost indicates the change in the objective function value, optimal objective function value per unit of change of lower bound or upper bound of a decision variable. If you recall, we said that for the binding bound, the reduced cost works. For the non-binding bound, the reduced cost or the marginal value of changing the non-binding bound, lower or upper bound, is 0. But also I mentioned to you the 100% rule, which is basically trying to help us to find impact of changes when we change multiple lower bounds, upper bounds, or also when we change right-hand side. So in this segment, I want to show you an example of use of 100% rule when we change more than one upper or lower bound or right-hand side of constraint. So here is an example question. What if lower bound for x1, for the first variable, increases by 10, and at the same time the number of pumps, right, and the number of pumps decreases by 20, right? And let's try to answer this based on Excel report. So now I have here a full sensitivity report for Excel, and I highlighted the relevant parts, right? So first of all, we can see that the final value of the first variable is 0, right? This is also shown here on the right, where there is the model and the optimal solution. And this is the smallest value that x1 can take, because the lower bound for all variables is 0. So it looks like, right, lower bound for x1 is binding, right, because x1 star is equal to 0. And the pump's constraint is also binding, right? Binding, right, because the final value of the left-hand side of this constraint, right? What's the value of x1 plus x2 plus x3, this part? The final value of this is shown here. It's 200, right? And it is also equal to the right-hand side, 200, or the right-hand side that we see here, 200, right? Okay. And you see the shadow price for this constraint is not 0, so this must be binding constraint, right? The same way as this lower bound 0 matches the optimal value of the variable, final value of the variable, and the reduced cost is not 0, this must certainly be binding. There is a case, by the way, if the shadow price was 0 here, this would mean that it might actually not be a binding constraint, it would be inconclusive, right? Because the slack is 0, and the shadow price, when the shadow price is also 0, it might happen in rare cases that the constraint is in fact non-binding, or it might be actually binding. At the same way here, if the reduced cost here was 0, we wouldn't be absolutely sure this lower bound is binding. But since the reduced cost and shadow price are both non-zero, we can for sure know that the lower bound here and the right-hand side here are binding. So what do we write from that? Right, we can tell what the marginal value of these binding constraints, limits are. Right, so the marginal value of changing lower bound of x1 or for x1 is the reduced cost, right? It is minus 50. We see it here in the report, in the first line of the first table, minus 50, and I will again put dollars per aqua spa just to emphasize that this lower bound is in the units, in the same units as the variable. It's in number of aqua spas, number of hot tubs of type 1 to produce, and so reduced cost tells us the impact on the objective, which is in dollars per unit of the variable, which is in aqua spas, or per unit of the lower bound. And right, and the marginal value of changing the right-hand side, that we're talking about, the right-hand side of the first constraint, the 200, right, is, right-hand side of the pumps, or of pumps constraint, let's keep it short, is shadow price the shadow price, which is here in the second table, the first line, 400, and again I will put dollars per pump, right? Again, the unit of the constraint is pump, and the unit of the objective is dollars, so therefore the shadow price must be in dollars per pump, dollars of profit per number of available pumps, per unit of pump, right? So, of pump constraint. So the next thing that I need to see is, well, these marginal values, how far can I use them? For how many units can I use them? So if you consider, right, if I consider what are the ranges of feasibility, well, Excel provides the range of feasibility for right-hand side, right? We can determine, we see here in this second table that the right-hand side is 200 and the allowable decrease is 50, right? And so this is the minimum value of the range of feasibility. And then if I take the right-hand side 200 plus allowable increase 8.125, right? I will get the range 150 to 208.125, right? So I could tell, for example, based on this range, that by decreasing by 20, 200 will give me 180. It will be within this range. So I could use the shadow price for if I were just to change the right-hand side. However, right, it will. The Excel does not provide, right, but it does not provide the range of feasibility of or for the lower bound, right? So even though we know the marginal value of changing the lower bound, of changing the lower bound for x1, we do not know the range in which this marginal value works, right? So even if I were to just change the lower bound, only the lower bound, and I wouldn't be able to tell if the reduced cost minus 50, this reduced cost minus 50, if it works for all the 10 units of increase of the lower bound of x1. I can only say this is a marginal value, at the lower bound. So this is the rate of increase, but I don't know for how long this is going to work. So if I do multiple changes and I want to use the 100% rule, the same way, I don't know the range of the allowable increase, right, that I need for the 100% rule, the allowable increase for the lower bound of x1. So based on Excel, basically, we cannot answer this question. We don't have all the data. Okay, so what happens when we try to look at the sensitivity report from Python, or for actually Gurobi obtained in Python? So if you see, right, I'm showing here the full sensitivity report. So the first part, if you notice, is about the objective coefficients and the range of optimality, range in which the solution will remain optimal if we change one of those objective coefficients. And then we have the part about reduced costs, right? So there is reduced cost minus 50 as before, and the range of feasibility for lower bound in which the reduced cost works. And the same here, the range of feasibility for upper bound. Upper bound is 150, and this is the range of feasibility 0 to infinity for the upper bound in which the reduced costs should work. So, right, obviously we recognize that the binding bound again is the lower bound, so the upper bound, when we change the upper bound within this range, the marginal value of changes of the upper bound would be 0, right? So we have the reduced cost and ranges of feasibility for lower bounds and upper bounds in the second table. And the third table, we show the large constraints, and we show the right-hand side and the range of feasibility for every right-hand side in which the shadow price, the pi, the dual value here works, right? So if we try to answer the same question using Python and Gurobi, the first 2 points are the same, right? The lower bound for x1 is binding, and the pumps constraint is binding, right? The final value is 200. So here we actually can see the slack, right? And then we know, of course, the shadow price is not 0, so this actually must be a binding constraint. Right, and again, the marginal value of changing the lower bound is the reduced cost. We see it here, minus 50. And the marginal value of changing the right-hand side is the 400, right? The shadow price 400. Right? However, in this case, right, we have the ranges of feasibility for both, right? So now we actually have all the information, right? We can tell that lower bound plus the increase, which is, right, the lower bound was 0 plus increase is 10, right? The lower bound increases by 10. This is 10, is within the range of feasibility for this lower bound, which is shown here, minus 32 to 20, minus 32.5 to 22, right? 10 is within this range, right? And also, the right-hand side minus the decrease, right? We're decreasing the right-hand side of pumps by 20. So right-hand side, which is 200, minus the decrease 20 equals 180 is within the range of feasibility for the right-hand side, which is shown here, right? This is from 150 to 208.125, right? However, if you remember, we're changing 2 parameters, not just 1. So this is not sufficient, right? Not sufficient information to decide if the change of the optimal objective function value can be calculated exactly using the reduced cost and shadow price. Right? This is not sufficient, right? We need the 100% rule here, right? Because we're changing more than 1. If we were to just increase the lower bound of x1, we know what happens. Reduced cost can be applied because we're within the range of feasibility. If we just change the right-hand side of the pumps constraint, again, we know what happens. You can use the shadow price because we are within the range of feasibility. But when you change multiple bounds, right, or right-hand sides, so this actually right-hand side is also like an upper bound on this function, right? So if we change multiple values like this, we need to use the 100% rule to know if the change can certainly be calculated exactly. So using 100% rule for the one that we updated, right-hand side, lower bound, and upper bound values, right? We can calculate the increase and the relative percentage, total percentage change that is calculated in relation to allowable increase or decrease, right? So we have first an increase by 10, right? So we have to take this increase, divide it by allowable increase, and sorry, I don't know what happened, but it's working again. And we have to add the decrease, right? So there is the second decrease divided by the allowable decrease for this right-hand side. So now notice, right, I mean, I don't have the Excel report now, so I'll actually have to calculate the allowable increase and allowable decrease from the ranges. So I will say, okay, the first increase is by 10, and what is the allowable increase for this lower bound? Well, since I know the value can go up to 22, that's the maximum value, I have to take 22 minus the current lower bound. So this will be 22 minus 0, right? So the allowable increase happens to be equal to the upper limit because the starting value was 0, right? And then the decrease is 20 for the right-hand side. And what is the allowable decrease? Well, I have to see these two values, right? It's 200 and the lowest value is 150. So the allowable decrease is 200 minus 150, right? So this is, of course, divide, right? So we have 10 divided by 22 and then 20 divided by 50. So one comment, right? I'm decreasing by 20, but still I'm adding here those changes. So don't put minus 20 by any chance here, right? It's even though it's a decrease, we just put the positive values here. Positive value of increase, positive value of decrease, right? So if you do the calculation, this happens to be around 0.4545, and the second part, 20 over 50, is exactly 0.4, so 0.8545, which is 85%, and that happens to be less than or equal to 100%, right? So now we know that the change of the optimal function value can be calculated exactly using the shadow price, the reduced cost and the shadow price, right? Because we are within the 100% of the changes. So let's calculate it now, right? So the optimal objective function value will be, right, what will it be? It will be the 83,000 that we had before, right? Let's write it, 83,000, right? And then we have to, we increased by 10 here, we have to put plus 10 times reduced cost, and then we decreased the right-hand side of the pump, so we have to decrease by 20 times shadow price, right? So this is important, right? When we were calculating the total percentage change, we had to add like the 20 and 10, both of them were positive. But because now we're calculating the impact of the objective function value, we have to consider that an increase of 10 in the bound increases 10 times reduced cost, the optimal objective function value. And then if you decrease the right-hand side, you subtract here 20 pumps from 200, then you have to subtract also here 20 times shadow price. So if you do the calculations, this is going to be 83,000 plus 10, and this is interesting, the reduced cost is minus 50, right? As we said earlier, the reduced cost is minus 50. So this is going to be actually a negative number, and then minus 20 times shadow price is 400, right? So in fact, this is going to be 83,000 minus $500 and minus another $8,000. So actually both of those changes have negative values. So at the end, it is going to be 74,500, right? Both of those will cause decrease. And of course, they cause decrease because both of them are restrictions, right? If we increase the lower bound of the variable that was 0, we're kind of forcing the solver to choose a solution where it produces the product that was actually relatively less profitable than the other options. And the same way, if we reduce the number of available pumps, we are restricting the problem. We're no longer having so many pumps. We have fewer pumps. And therefore, the achievable profit drops, right? So both cases cause reduction, right, of the profit. And then what happens to the solution? Well, given that we restricted binding constraints, right? Actually, both of them are binding constraints. And alternatively, I could say, given that the optimal objective function value changed, right? Both of those are good enough on their own. We can say the optimal solution must also change, right? Because, right, for the first one, if you restrict these constraints, well, the solution with x1 equals 0 is no longer feasible. It now has to be at least 10. Or the solution that is this. Remember, it was using 200 pumps. The slack was 0, so it was actually using all the 200 pumps. Now that we have only 180 pumps, because we decreased this by 20, this solution is no longer feasible, right? So even one of those constraints is enough to make the problem infeasible, right? And then the second way, so the optimal solution must change because it is no longer feasible. And the second argument, given that the optimal objective function value changed, right? If this value is no longer 83,000, it is now 74,500, but the objective coefficients, 350, 400, and 420, have not changed. So how can the value of the objective change? Some arguments here must change. If the coefficients remain the same, it must be that x1, x2, or x3, or a combination of them actually changes. And so we know the optimal solution must change in all those cases. So this is a demonstration, right? This was a demonstration of the 100% rule. And of course, I could have showed you examples where I just change multiple lower bounds and upper bounds, or I could show you examples when we change, let's say, one lower bound, another lower bound or upper bound, another right-hand side, right? Any combination of these highlighted numbers, lower bounds, upper bounds, and right-hand sides. When we change them, we can actually use the 100% rule. And as long as the total relative change of those coefficients does not exceed 100%, we know we can use right-hand sides, reduced cost and shadow prices to calculate the change in the optimal objective function value exactly.